In the next section of today's lecture, I'm going to move on and talk about multitask transfer. So this is the setting where we have multiple source domain tasks. So here's the question we can pose. Can we learn faster by learning multiple tasks? So let's say that you have a robot and you want that robot to learn how to cook a pancake and how to knead some dough and how to mix you a drink and how to do the laundry and whatever, right? So you have many different tasks that you want to learn. So you could learn each task individually, but that's going to be fairly inefficient because the training cost is essentially going to go up linearly as the number of tasks increases. And we know that DeepRL takes a while to learn, so this is going to be a while times 5. So the idea in multitask learning is, well, perhaps if we learn all these tasks together in a network that shares some representations, maybe all the different tasks can benefit from one another and therefore accelerate each other so that while you can't learn all the tasks together faster than you can learn a single task, maybe you can learn them all together faster than you can learn a single task times 5, essentially faster than just linearly sequencing the tasks. Now, intuitively, why might this help? Well, it might help because in the process of learning to, flip the pancake, you might acquire some visual features, representations, or behaviors that might also be useful for kneading the dough or folding the laundry. For example, maybe the robot that needs to fold the laundry has learned how to pick up an object, and picking up an object is really useful for also picking up the spatula and also picking up the bottle and so on. Now, this is not quite the same kind of transfer learning as what we discussed before. We're not talking about having a source domain and a target domain. Here, it's as though all of the domains are simultaneously both source and target, so they're all accelerating each other. Another way to think about it is that whoever makes more progress is kind of the source domain, whoever is slower becomes the target domain dynamically. In practice, the way we might implement this is we might have one neural network with multiple different outputs, multiple different heads, one for each task, and then the sharing of the representations inside the network accelerates the acquisition of all the tasks. But of course, you could also use this procedure in a traditional transfer learning setting if you, for example, have a sixth task, like using the sweeper to sweep the table, and the multitask learning serves as pre-training for that. Now, why might multitask learning be good pre-training? Well, for the same reasons that we discussed in the previous section, that when you have more diversity, more variability between the tasks, then you acquire more generalizable representations and maybe more diverse, more exploratory policies. Okay, so to summarize, you might want to learn multiple tasks simultaneously, both because that accelerates the acquisition of all the tasks that you're learning, and because it might provide a better initialization for then learning a new task. So both in the standard transfer learning setting and in this new notion of the tasks accelerating each other. And practically the way that you might do this is you might have a network where most of the network is shared between all the multiple tasks, but then there's maybe a different output for each task. Or alternatively, as we'll discuss later, you might have a setting where there's one output, but there's an additional input into the task that tells it which task to perform. Okay. So multitask learning can accelerate learning of all the tasks that are learned together, and it can provide better pre-training for downstream tasks. So can we solve multiple tasks at once, and how do we do it? Well, one observation that is pretty useful for this is that multitask RL actually corresponds to single task RL in a modified MDP, which I'm going to call the joint MDP. So here's how you can construct one MDP that captures multiple tasks. In a standard MDP, you sample your initial state as 0 from P of S0, then you take your policy, then you get S1, then you take your policy again, and so on. If you want to construct a joint MDP, you modify the initial state distribution and your definition of state so that the task that you're doing is part of the state. You can think of this as just an additional variable appended to the state. That additional variable doesn't change over the course of the episode, but it is sampled randomly for the initial state. So when you sample from P of S0, you really sample from among the different training MDPs. And in this way, all these training MDPs are basically combined into one joint MDP. So you basically pick the MDP randomly in the first state, and this is a well-defined Markovian joint MDP if the identity of the task is appended to the state. Okay, so that seems really simple. So then we could ask, well, why aren't we just all doing this? Like, why do we need to do anything else other than just embed our multiple tasks into a single MDP and just go for it? Well, it turns out that this way of doing multitask learning is just very difficult in practice. There are a couple of issues. One problem is sometimes referred to as gradient interference. Essentially, early on in training, you might be in a situation where the tasks aren't actually helping each other, but instead are hindering each other. So maybe becoming better at kneading the dough makes you actually worse at cooking the pancake, because you'll want to knead the pancake, and that'll mess up the pancake. So gradient interference basically refers to this issue where in the early stages of training in a multitask setting, if you use this joint MDP that I showed on the previous slide, you might actually get negative transfer rather than positive transfer. Negative transfer means that the transfer effect is actually hurting your ability to do the task. And this is a widely observed phenomenon. It's actually a pretty major challenge. The second and closely related problem is that in RL, you tend to have a kind of a winner-take-all problem. Imagine that one of the tasks starts improving a lot, whereas the other tasks are all doing pretty poorly. Well, the RL algorithm is then heavily incentivized to put a lot of emphasis on the task that's doing well and do it even better to further improve its expected reward, potentially at the expense of the other tasks. And this results in a widely observed issue where in multitask RL, one of the tasks will start learning and make a lot of progress, whereas the others will kind of get stuck. Now, I should say that both of these problems are, they're somewhat anecdotal. They've been observed very, very widely in experiments, but they're not very well understood theoretically. And there are a few guesses as to why they might happen, a few papers that speculate on these reasons, but there isn't a clear-cut, very concrete explanation for these issues, other than they seem to be very problematic and very common in practice. So in practice, this kind of multitask RL is very, very challenging. Now, there have been a few papers that try to address this with an approach based on training different policies for individual tasks and then combining them into a single central task with supervised learning. Let me discuss this approach and then we can talk a little bit about some of the trade-offs of doing it this way. So I've already mentioned these two papers briefly before, but I'll recap them again: Policy Distillation and Actor Mimic. And what these two papers aim to do is essentially train a multitask policy that can play multiple Atari games. And the way they do it is they train individual policies with RL, with regular single task RL for each game. And then they do supervised learning to learn a single central policy that plays all of the games. So the objective for training that centralized policy is basically maximum likelihood. So it's the expected value under the individual expert policies of the log probability of that action under the centralized policy. So it's just supervised learning. It's analogous to guided policy search, but for transfer learning. So I discuss this a lot more in the model-based RL slides. Another closely related algorithm, which I also mentioned before, is divide and conquer reinforcement learning, which learns these local neural net policies and then trains a single central policy with supervised learning. So again, I talked about this before. This was in the model-based RL lecture. These algorithms all have the same basic philosophy, which is that multitask supervised learning is easy, whereas multitask reinforcement learning is hard. So they'll do single task reinforcement learning, and then do multitask supervised learning to train a single multitask policy supervised by those individual local policies. Now, that said, these approaches do have a significant issue. And the significant issue is that, if we go back to this slide, if you're just training the individual tasks with single task learning, you're not really doing anything to alleviate the cost of acquiring those tasks by itself. So what these methods do to mitigate this problem is that they typically include some additional terms that also incentivize the individual task experts to resemble the centralized policy. And that creates a path for transfer between one task and another, so that if one of the experts becomes good, it trains the supervised policy to be better, and when the other experts emulate the supervised policy, they might get a little bit better too. So in the divide and conquer algorithm, this is basically done in the third line of the method, where the reward function for the individual local policies is actually modified to include this additional log pi theta term, which gets them to take actions that are similar to the centralized policy. So this basically attempts to put back in some of this transfer between the tasks. But it's far from perfect. Okay, so these are some results on transfer from the Actor-Mimic paper. So the blue line shows what happens when you share between the tasks, whereas the red line shows the single task learning process. And you can see that the blue line, in some cases, is quite a bit faster. All right, so the last question that I want to talk about for this multitask transfer discussion is, how does the model know which task to do? So in the Atari examples, it was maybe fairly obvious because you can tell from the image which Atari game you're playing. But in general, what if the policy can do multiple things in the same environment? So if you train up your robot and it can go do the laundry or it can go do the dishes, how does it decide which one to do? Well, as I mentioned before when I talked about the joint MDP, we need to provide an additional variable as part of our state which represents which task we're doing in order to make this a Markovian problem. When we do this, this is sometimes referred to as a context, and sometimes denoted with the letter omega. So here the context might just be a categorical variable that takes on two values, dishes or laundry, and you would basically concatenate this variable to the state. So contextual policy is just a fancy way of referring to a policy that takes in this kind of augmented state, or equivalently the original state, comma, context. So it's a very, very simple idea. So if you see someone say contextual policy, all they mean is they're just appending something to their state that tells the policy which task to do. And this could be, the location where the robot should stack the Lego block, the direction that the robot should walk, where it should hit the puck, whatever. Basically anything that uniquely identifies the task that it's supposed to be doing. And formally what that needs to be is something that is sufficient for the reward to be Markovian in terms of your augmented state S tilde. Okay, so that's contextual policy. It's a very simple concept. We will discuss contextual policies in a lot more detail when we talk about meta-learning, because one of the ways that you can cast meta-learning is as the problem of inferring the context, even when you're not given the context.